And hello, everyone, and welcome to the Sustainability in Energy Storage System webinar, organized in collaboration with the Haven, SMHYLES, and HiHELIOS EU-funded projects. We are very pleased to have you with us today. Before we begin, I want to thank you all for joining us. We truly appreciate your interest in the environmental dimension of energy storage technologies. My name is Camilo Borgoño, Head of Research and Development at AMIS, and I will be your host and moderator for this session. It's a pleasure to guide you through this joint webinar where 3 Horizon Europe projects come together to share their work on sustainability, lifecycle assessment, eco-design, and second life applications in energy storage systems. Today on the agenda, we have 3 presentations. First, Haven, focusing on sustainability and eco-design in hybrid energy storage systems. Then SMHYLES presenting their work on LCA and environmental assessment. And finally, we will have HiHELIOS, who will take us through second life batteries and life cycle impacts. After these 3 presentations, we will continue with a panel discussion and questions and answer session where all the speakers will be able to address your questions. Before we move forward, just a few practical guidelines. Please keep your microphones muted throughout the sessions to avoid background noise. You can type your questions at any time in the comments or chat section. And of course, all questions will be reviewed and addressed during the dedicated Q&A session at the end of the webinar. So feel free to write your questions as they come to mind. We will make sure they are covered during the panel. So now let's move into the core of today's session. We will start with the Haven project, followed by SMHYLES and then HiHELIOS. And with that, I would like to give the floor to our first guest, Carolina Fraga, Product and Process Development Engineer at INEGI, who will introduce us the information for the Haven project. So Carolina, thank you very much. The floor is yours and welcome.
Okay, Camilo, thank you for the introduction. I will just share my screen. It should be all right. If you can give me a heads up.
You're all set.
Okay, thank you. So thank you everyone for joining today. So my name is Carolina, and I will be talking about what we've been doing in sustainability in the project Haven. And first, to give you a bit of a contextualization of what the project is. The goal of Haven is to design a smart, modular, scalable, sustainable, and safe hybrid energy storage system with advanced cognitive functionalities and optimized high power and high energy capabilities. We aim to validate it and demonstrate up to TRL 7 in 3 physical and 1 virtual use case, covering a wide range of grid support services. And in the context of sustainability, our aim is to develop eco-design strategies and lifecycle data for comprehensive sustainability assessments of our system. And first, I would like to say that as we are still in the middle of the project, I will be focusing a lot more on the eco-design part, since it's where we have already completed our work. And the LCA part, I will just give you a bit of a hint on what's going on the project, but we do not have a lot of results for the system itself, so I will not get a lot of details on that part. But jumping a bit into eco-design, I wanted to show you first a bit of an idea of the whole process to get into the guidelines and how we developed the strategy to include not only a theoretical point of view, but also more of just so that we have more of eco-design strategy deeply rooted in practical knowledge. We include a lot of project technical partners in this whole process. And I want to give you a bit of a deeper details on this process, because I think that this process of getting to the guidelines is as much as a result as the guidelines itself. And I would like to first say that for getting to the guidelines, there were 2 important considerations in the beginning. First was, where is the systems and production process main impacts? Because we aim to understand what are the causes of the main impacts to be able to pinpoint where the guidelines should have a focus for greatest effectiveness once implemented. And the second, what are the obligations and recommendations for hybrid energy storage systems, since it's important to also have this part. So we looked into European initiatives so that we have also a legal compliance of the system. And for that, we ended up looking into both the literature and legal documents of Europe. And with a bit of this issue, and also kind of also taking a bit of the guidelines goals that we set, we arrived in some key topics that we considered, and they were really important for strategy throughout all the process steps to get into the guidelines, and they will keep showing up a bit here and there as I'm showing. So these are the 8 topics that we got from joining this knowledge of literature and legal obligations, recommendations. So we have these 8. And as I know I show you a bit of fast strategy, but after we went a bit into the literature and understood what were the strategies that we could find that were already being used in energy storage systems, not only hybrid, but also non-hybrid ones. We went with our first interactions with partners, with interviews where we were able to validate and also integrate a bit of new insights. So we got some eco-design strategies for the product, in this case, hybrid energy storage system. And those led us to our first guidelines. And as you can see, we have organized them by topics, as I mentioned. This is mostly because it would be easier for decision-making afterwards to understand where they would have most impacts. So you can see, for example, the battery components in chemistry selection would have great impacts on the critical raw materials, the recycling, and the environmental impacts topics, for example. And although they already gave us a bit of a good insights on where should we go for introducing sustainability into the design, they were a bit of a generical ones. So, and our goal was to take it in consideration of all of the specificities of the project system. So we kept working on it, and that led us to our next big part of the process, that was having a workshop before the project partners, where we, among a lot of activities, one of them was to identify some of their ideas that could be led to strategies to be implemented in the system, more detailed one, considering the background knowledge on the components they're working on. And not only that, we also asked them to kind of try to organize it in a matrix of feasibility and sustainability, just so we understand what they believed to be the most important strategies that came up in the workshop. And that got us into this kind of average positioning of each of the topics. And that would be used afterwards at the end, and I'll also bring it back, so keep that in mind. And then after this workshop, we got into our second interviews, where we took a bit of what was going on in the first guidelines and also what came up in the workshop. And we asked for these experts to put more of an additional details and try to make a bit more of a thought on where they would be applicable in the different components of our system. And that led us to the actual eco-design strategies for the HESS. But not only that, we also wanted to be sure that by implementing these strategies, we would have actual sustainable benefits. So we also did a bit of a study on some of the strategies, just so that we have these results, quantifiable results, that they were actually having a good impact. And I'm just going to show you 2 of the examples. We actually did about 6 of these studies. One of them was the second life application of the battery that came up as one of the strategies. And as you can see, by using a second life battery, we would have actually less impacts in terms of environmental impact, right? And other than that, we also did a bit of a study on the place the recycling should be done, where the recycling should be done. So we did a comparison between China, France, and Belgium. And we also saw that by maintaining the recycling within Europe, the results show that would actually have a good impact on sustainability-wise. And that's how we got into our final guidelines. As you can see, they were about 30 guidelines, so I'll not show all of them. I just brought a couple of them just to give you an idea. As you can see, we also kept the topics, so we still have this kind of way to know where the main effects are going to be on. And other than that, we using those average positions of the topics, as I mentioned, it would come up again. We use that to try to put it in do a hierarchization of the strategies. So you can see we base that on the average positioning of the workshop. And for example, the one that came up as the one that it had to be implemented as soon as possible is to use the dedicated chillers for its subsystem to simplify disassembly, reuse, and maintenance of cooling systems. And one that came up as not that important, but still would be nice to have implemented as well, of course, is in the case of the bus bars attachment, especially opt for welding to minimize material use and manufacturing steps. And now I'll just jump, as I said, to the LCA, and it's really initial work, but I think it's fair to show you what's going on Haven. For the LCA, we have this as a strategy. As you can see, we first jump a bit into the literature and try to understand where we stand, what is being done in terms of energy storage systems for LCA. So after that, we jump to defining our goal and scope. We also want to have involvement of the partners as they are data providers. So since beginning, partners are having a say on what they think is important to have as goals and what they think is important to consider for the baseline. Right now, we are about to submit our preliminary hybrid energy storage system, LCA and social LCA, but right now I'll only focus on LCA. And as I don't have that much data for LCA itself, since it's really preliminary work, I will focus a bit more on what is going on literature in baseline for this. And for the LCA, what we found in literature is that system boundaries are mostly used on cradle to gate and cradle to grave. As for function units, we see a lot of impacts per kilowatt hour of installed capacity or delivered energy or battery pack system. But on that term, when we're talking about hybridization of the system, as we have in Haven, it's important to take note that the capacity-based function units alone may underestimate the stability benefits of hybridization. So more of a service-oriented function units better capture these benefits of the hybridization. So we are taking that into consideration for our analysis. The most commonly used methods are RACP and YEF, and most assessed impact categories that we notice in the literature is the climate change, resource depletion, human toxicity, freshwater toxicity, particulate matter formation, and inflation. And also going a bit deeper now into what we found for results, the main impact drivers that we found was the raw material extraction processing, really connected to the critical raw materials that are contained in the electrodes of the battery. The battery manufacturing itself, since it's really high energy and has high material intensity, and electric mix during the operation also matters a lot. It can even make the use phase of the life cycle be a bit more intense than the manufacturing part, depending on how the electricity is handled. For life cycle hotspot, we see that upstream stages, as I was mentioning, dominate most of the studies. Raw materials, manufacturing, energy are the main ones, but transport not shows really minimal interference in the impact. In manufacturing is often the largest contributor across the impact categories. But other interesting insights, as I mentioned, the use phase can become dominant when fossil-based electricity is used. And the end of life normally don't have that much impact on the system. And jumping a bit into actual what's going on Haven, we have set as goals to identify sustainability hotspots through the system's life cycle, to assess impacts from the developed system, to establish the advantage and advantages of the developed system, and to assist in the achievement of the project KPIs. So not really breakthrough objectives, but it's important to take note on that and keep track on those. As for function unit, the process to define involved a bit of our partners, as I mentioned. So we got into 1 kilowatt-hour stored energy to be supplied. And for system boundaries, we went with cradle to grave assessments so that we could include also the use phase and the end of life, since we are also aiming to understand a bit better how second life batteries would be implemented in the system, could be implemented in the system. And also, as I mentioned, hybridization sometimes shows up as advantages when we are talking about the use phase, so that's important to be included. And the result that I can actually show you is related to our baseline that we define with our project partners, the data on past systems that they have developed. So we are talking about one that is 10 module configuration. We have the normal capacity of 50 kilowatt-hour. The cathode is LFP, and anode is graphite. And as you can see, not really surprising since we already got that from the literature, but cells are indeed the one that the components that have the most impact. And this, as you can see, this is really related to the critical raw materials and the intensity of the materials of the cells within the system. And the main impact categories that are shown here are the fine particulate matter, the human non-carcinogenic toxicity, and the global warming, which are due to the battery systems concentrating impact-intensive processes, such as the metal extraction and refining or the processing of these materials that are energy demanding and emit greenhouse gases and air pollutant precursors that impact the air, and that's why we see a lot of fine particulate matter formation. And that's all that I have to show you today. Thank you so much, and I hope I was a good presentation, if you were able to understand everything.
Thank you very much, Carolina. Quite interesting work you are doing in Haven. So we are going to continue with SMHYLE. I will give the floor to Viera Peshankova, LCA researcher at Thomas Bata University in Islim. So Viera, the floor is yours, and welcome.
Hello, everyone. Thank you very much for inviting me and also my colleague today to represent the SMHYLES project. My name is Viera Peshankova, and I will be presenting today together with my colleague Deboshri Paul. We are coming from the Tomáš Bata University in Zlín, located in the eastern part of Czech Republic, close to Vienna and Bratislava. The SMHYLES project is a consortium of a couple of interesting partners coming from across the whole Europe. The topic is related to safe and sustainable modular hybrid systems for long duration energy storage and grid services. So it's again, and similarly to previous Heaven project, a project related to energy storage systems in hybridized form. The coordinator is coming from Italy, Fondazione Bruno Kessler. It is running, or it has been running since 2024, and it will still last this year and also next year. The TBU, our role in the project is the lifecycle assessment as announced previously. So in respect to the presentation, we have divided together with my colleague, the LCA expert, Debashri Paul, the roles. She will be presenting the results of the environmental LCA, and I will provide you then towards the end of the presentation, the lifecycle costing perspectives and also some insights towards social LCA. So Debashri, please, the floor is yours now.
Thank you very much, Vera. I hope everybody is able to listen to me. I'm audible. Okay, so I will first start with defining what is hybrid energy storage system. So basically a HESS combines complementary technologies to optimize both power and energy delivery. So batteries provide bulk energy storage, and supercaps are able to provide or they are able to handle high power fluctuations or rapid cycling. And this load division can actually help in enhancing system efficiency, flexibility, performance, and also extend the system lifetime. So in SMHYLES, we see three specific technologies. First, we will see them at individual technology level, and then we will move to the demo site deployment where battery and supercaps are deployed together as a HESS system. So the first technology is vanadium redox flow battery, which is used for long duration bulk storage. The advantages include that it has the ability to decouple power and energy through independent scaling of stacks and tanks. And also it has aqueous, non-flammable, fully recyclable vanadium electrolyte, along with minimal degradation during deep cycle operation. The second technology is Zebra, or sodium nickel chloride battery, which is again used for scalable stationary storage. The advantages include no cobalt or lithium dependency. It's thermally stable at elevated temperatures, and also there's less thermal runaway risk when compared to conventional lithium-ion batteries. And finally, our third technology is supercap, which is used for high power rapid response. The advantages again include non-flammable aqueous electrolyte with very high, fast, ultra-fast charge and discharge response, and along with 98% efficiency and extremely high cycle durability. And together with this, this is deployed in our demo site. So our LCA assessment is in compliance with ISO 14040 and 44 framework, which has 4 interconnected stages. First is goal and scope, where we define the objective, system boundary, functional unit. Our second stage is life cycle inventory, wherein we quantify the material and energy flows. Third stage is impact assessment, where these flows are translated into environmental burden across 16 impact categories using the environmental footprint 3.1 methodology. And our final stage is interpretation, where we understand the hotspots, identify the hotspots, carry out sensitivity analysis, and finally draw conclusions. So for this study, we consider system boundary cradle to gate along with use phase emission. That means we have the manufacturing emissions and the use phase operation along with component replacement during the battery cycle life. And also, we use 2 functional units to quantify our emissions. First is the manufacturing emissions are expressed in terms of per battery system or per supercap module. And the second is to incorporate the use phase emissions. We normalize with the energy or the service that is provided in terms of per kilowatt hour of energy delivered over lifetime. Now, briefly, I just want to mention the LCI methodology. We have sent questionnaires for primary data to the manufacturers of VRFB, Zebra, and SuperCap. We've collected primary data from them, and the data sets which were not available, we consider the secondary data from literature. And of course, the background data is from EcoInvent 3.11, and we've considered for all three cases the same. And we've documented assumptions and limitations transparently, but I've mentioned some key assumptions here, which is relevant for our understanding the results. For example, we've used allocation methodology for our model for VRFB system, specifically for electrolyte production as system expansion with 97.5% of vanadium pentoxide purity. And also, if there is any component replacement required, we've also considered that during the cycle, during the entire life cycle of VRFB. And auxiliary roads are included in the round trip efficiency. For Zebra battery, along with the other battery and SuperCap, country-specific electricity mix is considered. For example, Zebra is manufactured by Sonic, which is based in Switzerland. So we've used Switzerland low voltage grid for manufacturing use phase at this particular single technology level. And also the operational losses, idle time losses, thermal energy demand for Zebra, everything is considered in the use phase operation. And also steady state operational performance is assumed over lifetime for Zebra as well as SuperCap, because we do not have the long-term degradation data. And finally, this is the configuration for the two demo sites, demo site 1, which has 3 VRFBs and 48 SuperCap modules, and demo site 2, which has 75 Zebra modules along with 60 SuperCap modules. So we will discuss this in detail during our demo site description. So now we will move to the results of VRFB, and before I move into the results, I want to mention that I will just cover a couple of indicators because of the time constraints and only mention the important hotspot that is driving the environmental impact for each of these systems. First is for VRFB, as you can see, for most of the environmental results are, I will just switch on the pointer. Okay, so you can see out of the 8 indicators, so 7 indicators, it is the electrolyte production, which is contributing to the environmental impact. And there are 2 reasons for this. Specifically for vanadium pentoxide production for the VRFB battery, we are sourcing it from South Africa. So it is produced or derived from the titanium ferrous magnetite ore. And it involves multi-step processes like, pre-treatment in a rotatory kiln, electric arc furnace melting, roasting processes. And these are all happening in South Africa, where the electricity mix is dependent on fossils, almost 85%. So this is one of the reasons. And the second reason is it's a low-grade ore. So for 1 kg of vanadium pentoxide production, we require 170 kg of ore. So having said that, also for VRFB, the mass, it is the electrolyte mass, which is like 75% is composed. So you can imagine how much electrolyte ore needs to be processed in order to provide this kind of purity of V2O5. As we see for all these impact categories, this is the reason why we have impact from the electrolyte production, except for resource use minerals and metals, where the impact is coming from the inverter because of copper intensive electronics, and also the printed circuit boards have gold and some metals which are contributing to this impact. Next is the use phase. We are carrying out the analysis of use phase. This is actually important variable because we can understand that the carbon intensity of the electricity demand is very important. For example, VRFB has a round trip efficiency of 56%. So a lot of charging electricity is required from the grid. So we have considered the baseline as German PV because it is manufactured in Germany. The Schmidt company is in Germany, and we consider Germany mix, and we consider 2 stress test like boundaries, with like one being with 99% renewable energies, that is the Norway electricity mix, and the second is Poland, which is 80% fossil mix. So it's clearly understandable that we cannot use VRFB for this kind of situation. VRFB is suitable for sites where there is renewable energy generation, because the use phase emission completely dominates the manufacturing emissions when we use this kind of electricity mix. And the second mitigation strategy would be electrolyte recycling. As we've seen in the previous slide, that electrolyte is the major dominant hotspot. So when we adopted recycling methodology from the literature, we could see that there was 43% reduction in GWP when we used recycled electrolyte. So the key takeaway message for this single technology is vanadium electrolyte is the dominant hotspot, and if you use renewable charging, it reduces CO2 emissions, and also electrolyte cycling can reduce 43% of emissions, GWP emissions. Next, we have Zebra technology. Again, Zebra is made up of components, many components which are made of nickel. For example, there's nickel powder, nickel carbon collector, nickel top plate, and nickel PCB seal. So for most of the impact categories like acidification, particulate matter, freshwater toxicity, human toxicity, as well as recursive metals, most of them are more than 70% contribution is coming from these nickel-based material because of the smelting of nickel, class 1 nickel. And the second most dominating component is the electrolyte production, as you can see, which is in green color for climate change and resource use in fossils. And this is because, again, the sintering, it's a ceramic electrolyte, sodium, magnesium, beta, alumina. It is produced by sintering processes, so which is extremely energy intensive, and natural gas is used for the sintering process. So that is why you can see the results in this way. A similar result was seen for the use phase analysis of Zebra battery, but since Switzerland has 60% renewable and 40% nuclear, for GWP emissions, we could see similar results as Norway, which is 99% renewable. But probably in the indicator of ionization radiation, we will see a different result. And again, we use two stress test boundary conditions of average mix, which has 20% renewable, 40% non-renewable, and 40% renewable in their energy mix. And with 80%, we could see it is completely overshadows the manufacturing. The use phase emissions completely overshadows the manufacturing emissions. And the mitigation strategy in terms of components for production, we used three criteria. One is using a recycled nickel and replacing electric sintering instead of natural gas sintering. And for production, we use Norwegian grid, which did not make much change because Norwegian and Swiss grid had almost same GWP production. But then with these changes, you could see there was a reduction of 40% in climate change. And also you can see in other indicators, there was a reduction in impacts. And finally, we come to the SuperCap results. SuperCap had a similar results as Zebra because, again, their important component was nickel-based, which is nickel electrodes, and also the terminals are made of nickel copper, nickel-coated copper. So these two contributed maximum together in all the impact categories. And for SuperCap, although energy capacity is quite less, but then because of the frequent cycling, the energy throughput across lifetime becomes very important. So again, if you use a fossil-based electricity mix, the use phase dominates the manufacturing phase. Else, it is always the manufacturing phase of SuperCap, which is extremely important when compared to the use phase. Another mitigation strategy was to use recycled nickel, as most of the components were made of nickel. So 50% nickel, we could see that there was a change in or reduction in most of the components, specifically acidification, because it reduces the SO2 emissions, which is generated during the smelting of nickel ore. Again, so now we finally come to demosite description. In demosite, which is a combination of vanadium redox flow battery and supercap, it is set in Sone campus, Portugal. Again, it has a system of 15 kilowatt medium voltage supply, a 1 megawatt peak PV plant, along with 250 kilowatt mini PV plant. We've sent in questionnaires for the demosite leaders, and also we have tried to procure the data for the components of the demosite setup. And this is the component level GWP, because as mentioned, there were 3 VRFP units, 48 SC modules, along with inverters and SC peripherals and cables, and also transport data was taken into consideration. So we could see the total GWP was around 490,000 kg CO2, with maximum coming from VRFP. As mentioned, why? Because of the electrolyte. A similar result was seen for the use-based results. As you see, a lot of energy is needed from the grid because of the round-trip efficiency of VRFP. So we could see with Portugal PV, we had 0.153 kg of CO2 across for 1 kilowatt hour delivered across lifetime. And this is based on the renewable grid. There's a Norway grid, which is 0.132. And again, with Poland, it was almost 4 times more. So the key takeaways of demosite 1, yes, PV charges performs best. Grid choice matters. Vanadium redox flow drives the GWP almost greater than 92%. And also recycling would transform the profile completely, and hybridization would optimize the roles across technology, because SC handles fast dynamics and VRFP provides bulk energy. And thus it would improve the operational robustness despite this kind of a conversion losses. And a similar result now for demosite 2, which is in Graciosa Island, Portugal. Again, you can see what they have in their island microgrid. It's an island with 4.5 wind and megawatt wind and 1 megawatt solar power. And again, with the similar key parameters and LCA methodology, we have generated the results for component level GWP, which was around 120,000 kg CO2 for the entire demosite. But here you could see that it is Zebra which is contributing maximum for the GWP, but also it is only 64%, unlike VRFC. But also there's a contribution from power electronics like inverters and process control system. A similar result was seen even for Zebra, again with the renewable charging with renewable electricity mix, and as a result you can see how this affects the manufacturing and use space emissions. And finally, the takeaway for demosite 2 would be it's suited for island grids, and also for Zebra battery auxiliary heating is critical, and that's why continuous high temperature operation requires constant heating. But Zebra dominates the system with only 62% impacts, and power electronics also contributes to the GWP. And again, here also hybridization enhances grid service capability. Now I will give the floor to Vera, the next part of the session.
Yes, I will continue smoothly with respect to life cycle costing and social LCA. I will try to be brief because we are indeed limited with the time. So the approach to reflect the costing or economy, let's say, assessment of the hybridized solution was in form of the levelized cost of energy storage parameter, and combined with Monte Carlo simulation, due to the fact that we had quite some uncertainty regarding the input parameters in terms of technological parameters, performance parameters, but also in terms of the cost components. So we performed 10,000 simulation scenarios with the help of the Monte Carlo methodology on this indicator of LCOS, and concentrated or focused on 4 scenarios. Then The first one, clockwise, A is rather pessimistic with low performance of the vanadium redox flow. Round-trip efficiency decreased to 50%, and then also supercap reduced recycling. Here we achieved the values around 0.12 euro per kilowatt hour in terms of vanadium redox flow batteries, and around 0.13 to 0.14 for the supercap. Then when we look at the scenarios B and C, when either no recycling credit was provided, or the capital expenditure was taken rather as a higher value or pessimistic value, for the scenario B or scenario C, where the cost was optimized, so rather optimistic scenario was there achieved. There is some shift visible in terms of the LCOS results. Interesting might be the scenario D, what we call combined best case, where we maximize the performance or the efficiency of the VRFB part of the hybridized system, and also try to work with relatively lower capex for the supercap. So this was the demo one insight in terms of life cycle costing, where we had the VRFB and supercap. Now on this slide, there are slightly different results, where the hybridization of the Zebra sodium nickel chloride battery with supercap is visible, and similarly to demo one, we have also 4 scenarios developed, where the ABC combination of different technological input parameters combined with different cost driver strategies, such as rather lower performance for scenario A, cost stress scenario for B, and cost optimized for scenario C. The last one, D, is the combined best case, where we focus on the rather optimistic round-trip efficiency of the Zebra with 90%, and the lowest capex for Zebra, and relatively low capex also for supercap. Here we are able to achieve slightly less than 0.05 euro per kilowatt hour for the supercap, and around 0.10 of median for the Zebra battery. And one of the last slides, it's related to social LCA. So here is an insight how we approached also social aspects of the developed solutions. We will not provide too many details on this side. This is an example how we try to capture the effect of the social risk categories and due diligence efforts combined on those different aspects. On this graph, we can see the social categories for respective life cycle stages pre-identified by consortium, because we performed also workshops and approached the technology developers with questionnaires. So there were some previous steps applied for the social LCA to pre-identify the relevant topics, relevant life cycle stages, and then to figure out which categories, social categories, which life cycle stages are the most material one, and figure out whether due diligence efforts have been applied and to what extent. So you can see, for example, child labor and forced labor received quite relevant scores in terms of social risks identified, and also some mitigation measures applied. Yeah, so in terms of social LCA, and now let me please summarize a couple of reflections on our work throughout the project. The first one is related to the material part or material supply chains, which are the major impact contributors. In respect to vanadium redox flow, it's obviously the vanadium pentoxide with some materials related to resource depletion, such as nickel or gold or copper, which was mentioned by my colleague Debusri. Secondly, the grid electricity mix is another important key message which can lead to substantial emission reductions. Of course, recycling is an important issue for all energy storage systems with quite major potential for reductions. The hybrid system, in principle, might demonstrate decarbonization potential, but of course, there are a lot of assumptions and limitations driven on one hand by efficiencies and technological developments, and on the other hand, also to downstream use phase operations. Yeah. And maybe one of the last points I would mention is the fact that the LCA work was performed in the initial design phase of the project, so a lot of uncertainties were just our common life. And some assumptions have to be taken into account in this case for all the three dimensions: for environmental part or assessment, for the life cycle costing, but also for the social LCA. So a lot of challenges across this pathway, and I'm sure we might spend another hour talking about all these challenges we had to take into consideration. So thank you very much, and look forward to the panel discussion.
Thank you very much, Viera and Debarchi. It's quite impressive, quite impressive presentation, and it's also quite interesting to see all these common points between the projects. And with that say, I want to remind all the audience to ask your questions in the chat. We will move to our last presentation, which is about HiHELIOS projects, and I will give the floor to Javier Gelamo, LCA researcher in energy systems at Vito. So Javier, welcome, and the floor is yours.
Yeah, thank you, Camilo, for the introduction. I will share my screen. Yeah, I think you can now see my screen. Yeah, so I will talk about the LCA activities in the HiHELIOS project. I will start by giving a brief introduction of the project, and then I will go through the different use cases, explaining the LCA approach we're considering for each of them, and then I will also present some preliminary results that we got for the use case 1, and I will finalize by presenting what are the next activities expected in the project in terms of sustainability assessment. So the main objective of the HiHELIOS project is to develop and demonstrate TRL7 modular hybrid energy storage system, HESS, as the other projects presented by my colleagues, by combining high power storage technologies with high energy systems. In our case, it's very important the use of second life batteries, concretely NMC, second life batteries from electric vehicles. And we have 4 use cases in the project: 2 EV charging stations, 1 in Belgium, another one in Norway, and then 2 other use cases that are implemented in the Tilos island in Greece. So I will focus today on the LCA activities, which is the topic of the webinar. So the main objective of the LCA in this project is to quantify the environmental impacts of the different use cases to ensure that the targeted system improvements do not compromise environmental performance. and also to assess the potential environmental benefits of using second life systems. So I will start with the use case 1. So the EV smart charging at Vito. We have a charging station in Energy Bill offices in Genk in Belgium. So currently we have just the charging station which is fed by the energy from the grid, and the objective of the project in this use case is to integrate a hybrid energy storage system consisting of ultra capacitor and LFP battery to increase the storage capacity of the system and also the power capacity. One of the main objectives of including this HESS system is to enable the use of solar energy in charging station to try to reduce the impact during the use phase. We are considering a cradle to grave approach in our assessment. So it means that we are assessing all these stages, the manufacturing of the HESS system, including the manufacturing of the different components. So in this case, the LFP battery and supercapacitor, and also the energy management system. Then we have the use phase, where the production of the energy that actually fits the HESS system is also included. In this case, we have solar energy and energy from the grid. And finally, we have also the recycling of the end-of-life systems, in this case, recycling of the LFP battery and the ultra capacitor. We are using this functional unit. The concept functional unit was already introduced by my colleagues in the previous presentation. So I will directly tell you what we are using. So we are considering 1 kilowatt hour of the total energy delivered by the system over the service life, which in this case is 10 years. So this means that we are calculating the environmental impact per kilowatt hour of energy delivered by the system during the total service life. And some of the environmental benefit or potential environmental benefit expected from the use case. First, as I mentioned before, increased use of solar energy should have an impact in the use phase, and also to have a faster charging by increasing the power capacity with the UltraCap, which would allow to charge more cars per day, which means that more energy is delivered by the system. And since we are distributing the impacts by the total energy delivered, they should also have an effect on the final environmental impact. Then we have the use case 2, which is very similar to use case 1. Again, EV charging station. This one is located in Norway and is led by UNOX company. Same approach than in use case 1, but in this case, the hybrid energy storage system is composed of LTO battery to combine with a second life NMC battery that is coming from electric vehicle. Same objective as in the previous use case, so enable the use of solar energy and to increase the power capacity of the plant. In this case, we are also considering the manufacturing, use phase, and end of life, with a small difference in here. As you can see, we are assessing the manufacturing of the second life NMC battery. So to do this, we are using allocation approach, which means that we are not accounting for the whole impact of the manufacturing of the battery, because it's using 2 stages, first life and second life. So we are allocating the impact from the manufacturing into the second life. And how do we do this? So we are doing an allocation considering the energy delivered by the battery in the first life and in the second life. So I can better explain it with a small example in here. So if during the first life, the battery delivers, let's say 6,000 kilowatt hours, and during the second life, 4,000 kilowatt hours, it means that 60% of the energy is delivered in the first life and 40% in the second life. So if we have these requirements for the cell battery production, 10 grams of nickel oxide and 2 kilowatt hours of energy, if we perform this allocation to the second life, it means that we would have we would account for 4 grams of nickel oxide and just 0.8 kilowatt hours of energy. So basically 40% of the initial requirements. So yeah, this is the approach we're using for modeling the second life system. So we have the allocated impact of manufacturing, first life manufacturing, let's say. We are excluding the first use phase. And then we have the collection of the end-of-life system, then the testing and repurposing to create the second life system, the second life use. Again, end of the second life collection and transport, and at the end we also have the recycling of the second life battery. We are considering the same functional unit as in the previous use case, so 1 kilowatt hour of the total energy delivered during the service time of the charging station. And again, the main objective is to increase the use of solar energy and also to have faster charging to increase the total energy delivered during this time. Then we have the use cases 3 and 4 that I'm presenting together because they are quite similar and they take place in the same location. So in the Tilos Island in Greece, there is currently a power station in there consisting of some renewable energy generators, basically some wind turbines and a solar plant. There is also a battery and there is a diesel generator. It's connected to the grid and it's supplying the energy to the whole island. So in this case, the idea is to integrate the hybrid system consisting of LTO battery plus, again, the second life NMC battery for the use case 3 and a sodium ion battery plus the second life battery for the use case 4. And the idea is to increase, in this case, the storage capacity to also increase the amount of renewables that can be used and reducing the energy delivered by the diesel generator to have a more attractive environmental performance and also a higher grid stability. Again, we are considering all the stages in the assessment: manufacturing, use phase, and the end of life. And for the second life battery, same approach as before. Yeah, again, functional unit to make it comparable. We are using 1 kilowatt hour of total energy delivered by the system over the service life, which still needs to be defined in this case. And some of the environmental benefits expected for implementation of this use case. First, increased use of renewable energy, as I mentioned. Also reduce reliance on fossil fuel generation. Improves energy efficiency, so less losses during the use phase, and also reduce need for grid infrastructure expansion compared to the benchmarks. Now, I will present some of the preliminary results we got for the use case 1. This project is now ongoing, so we are like in the middle of the task and also in the middle of the project. So we don't have final results for any of the use cases, but we got some preliminary results for use case 1 based on different assumptions and some literature data. So I will introduce these results, but yeah, we will have final results in the future to have clearer pictures of the different use cases. So some information about the model, as I mentioned, cradle to grave approach and this functional unit. Well, we are using equipment 3.11 as a background database and environmental footprint method. We have assessed 3 different scenarios, 2 benchmark scenarios and the use case scenario. So the first benchmark is the one I introduced at the beginning, which is the current status of the charging station, just the charging station fed by the energy from the grid. Then one benchmark which introduced one battery to enable some use of solar energy. And then the use case scenario, which includes the hybrid energy storage system with the supercapacitor and LFP battery, also to enable the use of the solar energy. So in here, you can see the results just for the global warming potential, so the carbon footprint per kilowatt hour. Something important to mention here, the expected use of PV, according to some estimations from the Vito colleagues implementing the use case in Belgium, around 12% of energy from the total energy use will be coming from solar use. And with this assumption, we got these results. So what we can see is that in the use case, there is an increased impact related to manufacturing, which makes sense because now we are considering the battery and the ultra capacitor of manufacturing. There is a reduction in the use phase impact, which is due to the use of solar energy. Also negligible impact of the end-of-life processing. There is a small line here. I don't know if it's visible, but yeah, it's negligible compared to the other stages, the recycling processes. And overall, we can see a small increase in the environmental impact of the use case 1 compared to the current status, the benchmark 1, but a reduction compared to the benchmark 2, which is using one single battery instead of the hybrid system. The use of PV is a parameter that has some room for improvement. So we also conduct the assessment considering a higher use of solar energy enabled by the battery systems. So if we have a 20% of use of solar energy, then we can see that actually the use case 1 has a lower impact than the current benchmark, which is due to the further reduction in the use phase impact. And again, a lower impact than in the use case using just the single battery. As I mentioned, these are some preliminary results we got so far, but we will have final results soon, so we will be able to make more clear conclusions after that. And what's coming next for the LCA activities in the project? So we will finalize the models for all use cases. Also assess different impact categories beyond global warming potential, of course. We'll conduct some sensitivity analysis for some parameters that can influence the overall impact. As we just saw, the solar energy use is one that we want to assess. And we will also have a prospective assessment to assess what would be the potential future impact if the use cases is implemented in the future. So yeah, that's it from my side. This is my contact information and also my colleague working with me in the project. So if you want to reach out to us, please feel free.
Thank you very much, Javier. Quite interesting presentation. Now we will move into the panelist session where all our speakers from HAVEN, SMHYLES, and HiHELIOS will join us for a collective discussion. So before jumping to this, let me introduce you our panelists. We're going to start with the HAVEN project members, starting with Carolina. Carolina Fraga holds a bachelor and a master's degree in environmental engineering from the University of Porto. Her work focuses on sustainability with experience in life cycle assessment and eco-design applied to energy and battery technologies. At INEGI, she contributes to battery-related European projects through dataset development, environmental assessment, and the integration of eco-design principles into the evaluation of emerging technologies. Then we have Leticia Castrejon from Bring. She's a technical project manager at the Brussels Research and Innovation Center for Green Technologies and project coordinator of HAVEN. She holds a master's degree in electrical engineering with a specialization in photoelectrocatalysis for hydrogen production and sustainable energy systems. She brings more than 3 years of experience working on Horizon Europe projects. Then we already heard about Javier Gelamo Mayorga. Javier is a chemical engineer with experience in life cycle assessment and battery recycling technology. He currently works at Vito as an LCA researcher for energy systems. And from the SMHYLES project, we have Viera. Viera serves as a researcher and a project manager at Thomas Bata University in Slin, specializing in life cycle sustainability assessment and sustainable battery technologies. Her work connects environmental, economic, and social assessment methods with emerging energy storage systems and responsible innovations. She coordinates and contributes to several Horizon Europe projects and actively promotes the integration of social science and humanities into battery research and policy. And then we have Debashi Paul. She earned her PhD in chemical engineering in 2021 with work in nanobiotechnology and has been a postdoctoral researcher at Thomas Bata University in Slin since 2022, specializing in environmental life cycle assessment. Her research focuses on evaluating the environmental impacts of technologies, particularly in energy systems and batteries, including the life cycle assessment of bio-based technologies to support sustainable development. She has served as a core LCA researcher in multiple Horizon Europe projects, contributing to sustainability assessment. That said, I will start with the questions that we have from the public, and let's start with a Haven project. So I will read the first question, and we will get the answers here. Okay, Haven has developed eco-design guidelines to embed sustainability directly into the HESS design process. Can you share a concrete example of how these guidelines have translated into specific engineering decisions, for instance, regarding material selection, system architecture, or component sizing?
Yeah, of course. Yeah, one of the the cases that we have discussed that I've been most requested in this was regarding the selection of refrigerants for both the high energy and high power energy batteries pack. The decision was not only done by performance, but also it took a lot of consideration what were the global warming potential of the refrigerants. Also because they are kind of being regulated more heavily now from the European point of view. So we also had that as a strategy for our guidelines. So this was one of the more discussed cases in Haven.
Perfect. Thank you, Carolina. Now moving from the eco design to LCA, your LCA follows the ISO 14444 standard and covers the full value chain from raw material extraction to end of life. At this stage of the project, what are the key environmental hotspots you have identified and how they are informing the design choices made by your engineering partners?
Yeah, I mean, as I said, importantly, we don't have that much knowledge on the actual system since we don't have that much data for the final system yet. But I could say that it's shown in the literature and the baseline that the batteries tend to be one of the major impact drivers. And we are avoiding actually, for example, cobalt intensive chemistries for these batteries. So we are already in a kind of an advantage. And this was actually one of the strategies as well for the guidelines to the choosing of the chemistries for the batteries. So this is kind of how it's related, is being related to the actual impact of the systems.
Okay, perfect. So I think we will get more answers by the end of the project on this one. We have another question. It says, Haven aims to extend the useful life of components containing critical raw materials through second life applications and critical raw material recovery strategies. How do you determine whether a component is better suited for a second life use case versus direct material recovery, and what criteria guide that decision?
I think firstly it depends on the conditions of the component, which I can say for this specific question, I think it's way more related to the battery, since it's where the critical raw materials are more concentrated in the systems. And from my past knowledge, I would say mostly it's more advantageous to have second life applications when possible. So I mean, I think the actual determination of which of the cases can be a bit more of a technical choice than only the sustainability part. But if you can have both choice and they based only on sustainability point of view, I think using it in second life as well mostly be better than just the reintegration of the materials itself.
Okay, perfect, Carolina. Thank you very much. We will move to Project SMHYLES, and then I think we have one last question for Haven. We will do it later. So we got a question for SMHYLES from the audience, and a comment that followed that questions. The question was, recycling the electrolyte also requires additional recycling processes, such as distillation, which consume electricity. Is this also taken into account? And then we had a comment in the chat that said that it seems that the analysis is cradle to gate. So in that case, the recycling phase is not included in the LCA analysis. So the question will be whether the recycling phase is included, and if yes, are recycling processes as distillation taken into account?
Yes, thank you very much for the question as well as for the comment. Actually, the comment actually answered partially the question.
Yes.
It's true that our system boundary is cradle to gate, as in we have considered manufacturing emissions. And the recycling part that we mentioned is more like, it's an alternative production stage supply scenario. As in, we are not considering the entire end of life phase of the battery, but just of the component. Like, for example, for VRFP, it was the electrolyte, which has maximum hotspot. So that's why we just considered if we can replace like the 100% primary electrolyte with a recycled electrolyte, what would the result look like? And we've also mentioned in one of our limitations that we, because it's still an ongoing, like in our project, one of the demo site leaders are still working with the recycling process. So we have simplified our data and conducted this recycling in terms of for vanadium redox flow battery as well as for recycled nickel. Again, that's again a secondary data set, just to see if you use, for example, primary nickel in Zebra battery versus like a recycled nickel, what would the production impact look like? So it was just like an alternative production stage supply scenario. So we only have cradle to gate and use phase considered. I hope that is clear.
Thank you, Debashri. We have another question for SMHYLES, and is from an LCA perspective, which technology improvements or system integration strategies are likely to deliver the largest reduction in life cycle environmental impacts for hybrid energy storage system going forward?
Yes, I would say that our LCA study has identified opportunities across both manufacturing and use phase. For manufacturing, I would say it's very important to have this material circularity, especially that I just mentioned before regarding the electrolyte recycling, because that is our dominant hotspot. So it would be extremely efficient if we can use or recover vanadium from the spent electrolyte. And also, since we are using electrolyte, like primary electrolyte, which is sourced from titanium ferrous magnetite ore, if we are able to replace some of it by, electrolyte from spent catalyst, so that would majorly improve the environmental hotspot in terms of electrolyte for VRFB, because in Demosite 1 and in Sengal technology, it is the electrolyte which is the dominant hotspot. Similarly, for Zebra battery, it is the electrolyte, which is sodium, magnesium, beta, alumina. If we are able to have the electric sintering process instead of using the natural gas, we can reduce some amount of environmental impacts, GWP emissions. And another important point is the use phase for vanadium redox flow battery, because we have very low, we have round trip efficiency of 56%. So if in any way we are able to improve the stack design or membrane performance or electrolyte flow management, somehow we are able to reduce the losses that is happening in the charging losses, then we are directly, we can reduce the amount of lifetime energy demand for the system. And of course, the third point is we've already established renewable electricity with hybrid system integration. That is also one of the key improvements for with the largest reduction of environmental impact.
Okay, thank you very much for your answer. I will move to HiHELIOS. We have a question for Javier, and this is a question from the audience, and it says, why does use case 3 and 4 has sodium nickel chloride, sodium ion, and lithium nickel manganese cobalt oxide batteries all together in the single frame?
Yes, so that's correct. Currently, in the use case in Greece, there is one battery, which is this sodium nickel chloride. But the size of the battery is quite small, so the capacity it's very limited, which means that the use of renewables it's also limited by this. So the idea is to integrate into the power station an additional storage system, which is the hybrid system that has these two other elements, the sodium ion plus the NMC battery. Actually, it's not sodium ion. In this case, will be LTO battery plus the NMC battery. For the use case 4, because I combine 3 and 4, can be a bit confusing, but in the use case 4, it will be sodium ion plus NMC in a smaller size. But yeah, in the use case 3, in addition to the sodium nickel chloride, there will be the hybrid, which is composed of the NMC plus LTO. So the main reason is to increase storage capacity and to ultimate increase the amount of renewables that can be used.
Thank you very much, Javier. Now that we are talking about NCM batteries, we have another question. It says, HiHELIOS use second life NMC batteries as the high energy component of its hybrid energy storage system. From a life cycle perspective, how do you account for the environmental burden of the first life of these batteries, and what allocation methodology are you applying to fairly distribute the impacts between the first and the second use?
Mm-hmm. Yeah, so I introduced this during the presentation. So we are using an allocation approach, which is based on the total energy that is delivered during the first life and the second life, which means that to assess the impact of the second life, we are accounting for a portion of the impact of the manufacturing, not the whole impact of manufacturing. And how we do this allocation? So as I mentioned, we first estimate how much energy is delivered in the first use, how much energy is delivered in the second use, and then we allocate this total impact of manufacturing based on these ratios. So for instance, if we have 60% of the energy delivered in the first use and 40% of energy delivered in the second use. Then in our model, we will account just for the 40% of the manufacturing of the battery. So we do account for manufacturing at the first life, but using this allocation approach based on how much energy is actually delivered on each stage.
Okay, perfect. Thank you. And regarding you mentioned that you have 4 distinct use cases. What are the most significant environmental differences you are observing across these use cases? And how does the operational profile, including depth of discharge, number of cycles, and grid electricity mix, affect the overall life cycle results?
Mm-hmm. Well, we still don't know what will be the actual environmental differences between the different use cases because, as I mentioned, the LCA activities are ongoing. But indeed, we can see that the different use cases have different applications and different use profiles. And this will result in different lifetimes and different total amount of energy delivered. And since we are using the same functional unit for all use cases, which is 1 kilowatt hour from the total energy, if we have different use profiles, it means we have different amount of total energies, and then the total impact would be distributed within a different amount of energy. So that will have, of course, an influence on the impact. So that will be an interesting assessment that we will do, compare different use cases to see which applications are more beneficial for the hybrid systems, because in some cases the lifetimes will be higher than the other, so the impact might be reduced by this extended lifetime. But yeah, this is something that we will see when we have a clearer picture of the overall results later in the project.
Thank you very much, Javier. And of course, we look forward to seeing these results in the future. We have what we could call some cross-project panel questions. I have one question. Any one of you can reply to this one. Let's try to keep it short for the sake of time. And the question is, each of your projects is working towards a battery passport, a digital record enabling traceability across the full value chain. What data are you currently collecting that could feed into a battery passport for second and third life batteries? And what regulatory or technical gaps still need to be bridged? This is another question for any of the panelists.
I can maybe start.
Yep.
Yeah, so well, when in our project we have one specific task working on the battery passport development, led by my colleagues from ROI. Would be interesting to maybe have a dedicated session on that topic as well. But from the LCA part, some important data that we are collecting and we think they need to be included in the battery passport is data related to the use phase of the battery, related to the state of health of the battery. In the project, we have access to this data because the battery supplier is part of the project, so we have access to it. But maybe in a let's say real world application, it might be more tricky to get this kind of data because it depends on accessibility to the BMS, to the battery management system. So I think this is something to look into, at least in our project, the people working on the development of the BMS and the EMS, how this data can be accessible at the end of life to be then included in a battery passport. So yeah.
Thank you very much, Javier. We have another cross-project panel question here, and I think this is a friendly one. Looking across all the 3 projects, you are each applying LCA to quite different storage chemistries and use cases. What shared methodological challenges have you encountered, for example, around data availability, system boundary definitions, or end-of-life modeling, and how are you addressing them?
Maybe I can reply to this question from and on behalf of SMHYLES project. In our case, we tried to apply kind of integrated LCSA methodology, which is combination of environmental, economic, and social LCA, as you might have understood. And this combination is even multiplication of different kinds of challenges. So speaking about ELCA or the environmental part, of course, and this is common maybe to all the three dimensions, it's about the data accessibility and response from the technology developers, and also combined with some data uncertainty. That's why we introduced into calculations also probabilistic modeling, and some support from not only primary data collection, but also secondary data from, of course, we know different databases for environmental LCA, but also for social LCA. What I could mention else is in general the problem or the challenge moving from environmental LCA to cost and social perspective. You are moving from quantitative or more of a quantitative way of modeling towards more qualitative aspects and modeling, and this itself is really a challenge. And then the combination of those different kinds of results, partial and preliminary results from these three dimensions, is another issue where you end up with different kind of scenarios and face a decision-making problem where I think the methodology such as multiple criteria decision making might be helpful. But this is something we have not applied yet, but it's for sure a pathway or a way how to handle different criteria and different results with different weights, different stakeholder perspectives. So let's say briefly the insight from our project.
Yes. Thank you very much, Viera. We actually have another question for SMHYLE project. And the question is, life cycle assessment of integrated hybrid energy storage systems requires combining data from multiple technologies, manufacturers, and operational scenarios. What were the most significant challenges in collecting and harmonizing the data needed to build a credible LCA model for the SMHYLES project?
Yeah, so I could probably answer this question, and Vera's covered like the maximum gist of it. But also additional challenges, I would say that since the project was like mid-level LCA data collection, so there were a lot of challenges in understanding the operational data or the data collection for different demo sites, the peripheral components. So a lot of it was based on engineering assumptions rather than real-time measured data. That was one challenge. And second challenge was, for example, the vanadium redox flow for the VRFB battery, the vanadium electrolyte, or the vanadium pentoxide production. We had to depend like on data sets based on secondary data where different kinds of allocation strategies were used, and each allocation strategies had different kinds of results. So our equipment database, where we use background databases, we do not have this kind of data, so it becomes a bit challenging to understand the impacts of the choice of what data would you choose for your electrolyte production. And finally, I would say about data harmonization across consortium also required a significant amount of effort, because the different kinds of like data format or data detail or engineering assumptions were quite different for each of these technology. And so to align all these assumptions and system boundaries and inventory structures across single technology, across the demo site, and across this environmental, social, and economic sustainability assessment, it required like considerable amount of work. So that was our like challenges.
regarding this particular study.
Okay, thank you. Thank you very much. Thank you to all of you. As it's almost 15:30 now, and as we come to the end of today's webinar, I want to thank you all for joining us and for your active participation. A special thank you as well to our speakers from the 3 projects for sharing their insights and contributing to a very rich discussion. We hope this session has given you a clear view of sustainability challenges and opportunities in energy storage systems and of the important work being carried out across these 3 Horizon Europe projects. To stay updated on our next webinars, events, and project development, we invite you to follow our projects online. You will also find links to our social media channels on each website, where we regularly share updates, results, and upcoming activities. Thank you once again for being with us today. We look forward to seeing you at our next webinar. Have a great afternoon.
Thank you.
Thank you so
Bye.
much. Bye.